Good afternoon, everyone. So I'm Tilloy, and I'll be chairing this post-lunch session today. So welcome to all of you. Welcome all of you to this session. And the first speaker of this session is Antoine Tilloy, and he's going to talk to us about digitized continuous quantum trajectories. Over to Antoine. There is a time for you.
Thank you very much. So first, I'm really happy to be here. I was here 8 years ago, and it's amazing to see how much the campus has changed. For the best, so now there are trees. I wonder how it's going to be the next 8 years. And I really also enjoyed the talks. So today, I will talk about an extension, sort of this theory of quantum trajectories. It's work done in collaboration with these two collaborators in Paris, so Pierre Rouchon and Pierre Guillemin. They both gave a talk already, so you know them already. They need no more introduction. So let me start right away. Fortunately, in this conference, I need only a very minimal introduction to continuous measurements, since it's more or less like quantum trajectories are the subject of the conference. But the picture I have in mind is that we can derive continuous trajectories from the continuum limit of repeated interactions, where you send probes to a system and they weakly interact with it, and later on we measure them. And there is a smart scaling limit where we send these probes faster and faster and have them interact weaker and weaker. And in the continuum limit, there is no Zeno effect, but there is a new time scale associated to measurement. And I think Pierre showed a fairly similar drawing. So from these discrete trajectories, if you take the continuum limit appropriately, you get a continuum trajectory in the Hilbert space, at least in the diffusive case, that looks more or less like a Brownian motion. So I think I'll say it again, but today I will talk only about continuous measurement in the diffusive case corresponding to homodyne detection, but everything I will say could essentially be extended easily to heterodyne or jump case. Okay, so that's the picture, and this was explained in several courses, probably Pierre's talk at Pierre's course on the very first week, and it was reused by many other people here. And at the end of the day, what you get is what's called the stochastic master equation, which is a stochastic differential equation with a deterministic part corresponding to the usual Lindblad part we are used to, and an extra measurement back action term that depends on the signal. And this signal also obeys a stochastic differential equation, which has a deterministic part depending on the quantum state itself, plus some Wiener noise. And the signal is really a fully continuous object, okay, that can, in principle, be fine-grained with arbitrarily small time bins. And so again, today I will talk about only the homodyne detection case, but everything I say could be applied to various measurements in parallel even. Okay, so measuring several operators with different unravelings. Okay, so that's the basic theory, and I think by now we are quite familiar with it at the second week of this very nice conference. But I would like to talk about a particular imperfection in practice that is, in fact, very crucial, I think, which is that this sharp signal that has the regularity of white noise, okay, that I drew just before, is not empirically accessible. And there are essentially two reasons for it. The first is that I cannot even plot it. So already this is a discretized version of the signal because the true signal has a regularity of white noise. So I cannot even plot it. It is a distribution in principle. And there is a more practical reason for why this sharp signal, this continuous time signal doesn't exist, is that in practice, we can only store a finite amount of information, so store its a discretized version on small bins. And so I'm, again, reusing something from Pierre's slide, and also I think Benjamin Huard showed similar drawings. At the end of the day, there is always this ADC, okay? We are converting this analog signal into some discrete series of measurement results. And that's all we have at the end, okay? We never really process this continuous object, the signal, even though all the theory is made around it. And so this leads to another sort of a new picture, which is we had the discrete time picture. We take a smartly a continuum limit that gives us a continuum description of measurement that we think is what's happening really in the experiment, or at least that's a very good approximation of what's happening in an experiment. And then on top, we digitize this. And so we get effectively a new discrete trajectories, but this time they are the discretized version of the continuous time dynamics. And so they are different, okay? It's like this is a new thing. This is a new object, and what I would like to argue is that these are really the quantum trajectories we have in practice, even in the continuum case. Okay, they are these discretized continuous time trajectories. In practice,
quick question.
Yeah.
Are these mappings one-to-one? So given a discrete time trajectory, is the continuous time trajectory unique? Given a continuous time
there are various ways to take the continuum limit, but if you specify well what you mean by the continuum limit, certainly like this goes only one way. And then digitizing, once you specify how you digitize, I mean, certainly it's one way.
So this process is a deterministic process, the digitization.
Yeah, digitization is, you just average the, I will say a bit more, but you average the signal over time bins. Okay, there is no, yeah, what to say is there is no extra randomness in principle associated with this mapping here. It's a deterministic one, right? It's just an averaging in time, not a stochastic averaging. Okay, and so this is really a problem in theory and practice. So the fact that we don't have this signal, but rather discrete results on bins. And if you look at what's mostly done currently, and by what's mostly done, I mean really what even we ourselves are doing, okay? What's done in experiments when we do the theory for experiments at ENS or in Alice and Bob, but I guess that's what most people are doing. We just reconstruct the state as if we had the real continuous dynamics. So we pretend these are actually continuous outcomes and that they are taken over, they are averaged over a time bin that is small enough that we can approximate the true signal by this type of finite difference. And then we feed this measured signal directly into the continuum stochastic differential equation, discretized with one of the schemes available. We make a mistake by doing this, okay? This is not a true continuum signal, it's a discrete one. But what you can do is push the analog to digital conversion to very, very small time bins, such that your discretization error is as small as possible, okay, so that you're very close to the continuum limit. But this comes with several issues. So the first is that as we probe in experiments faster and faster timescales by driving super strongly, for example, we start to encounter timescales where this delta t, this digitization timescale, is no longer super small. It's no longer orders of magnitude smaller than all the other timescales. Further, if you take delta t very small, you quickly generate a ton of data. So if you take one data point every nanosecond, you have 4 gigabytes of data every second. And quickly it becomes a problem, especially these days people, for example, at ENS or in Alice and Bob, are estimating bit flip times with quantum trajectories. These bit flip times are sometimes in the order of hundreds of seconds. So imagine the amount of data that you have to store to reconstruct a quantum trajectories of a few hundred seconds if you bin at a 1 nanosecond scale. And also there is a problem theoretically. Theoretically, this is not really satisfactory, that there is no way to sort of know what error we are doing by making this. Like, I would be fine to use this process if it could be refined in principle to be better and to give us a better defined quantum state. So doing this is not very principled. That's what I'm. Okay. And so for this problem, I don't know, maybe one more thing to say is that in particular, something we have seen in practice is that tasks like parameter estimation and max-like tomography can be really sensitive to this delta t. So the fact that in practice, doing this is a bit wrong, we see that it really damages our parameter estimation and our max-like tomography, especially for cat qubits, for example. So it's not just a pure theorist problem. And there are two solutions, I think. So Pierre presented the first one, which is, okay, drop the quantum state, drop the stochastic master equation even, and just try to extract as much as you can from correlation functions of the signal itself, of these time bins. These are computable exactly, so there is no theory issue around it, and use it to extract your system parameters or everything you can. But now in this, and this is a very, it's a very nice way to do it, and in this talk today, I would like to present an alternative, which is to really construct the cross map associated to a finite time bin. Okay, so we are back to, once we discretize on a time bin, we are back to discrete quantum trajectories. For a well-defined discrete quantum trajectory, I should be able to define a cross map. And then the right answer, how to reconstruct the state, is just to compute this cross map. So you can understand this talk as an explanation of how we can compute this cross map. So the setup really is the following. Yeah.
And in the beginning, you started from a discrete map, and then because in the experiments, actually, you do a discrete time, right?
Yeah.
So and could not, and one could have just stuck with the original cross maps, and not first go to the continuum limit and then again go back to the discrete.
But this is not what people have in experiments. So people in experiments really have the average of something that is well approximated by the continuum. So it's really, this cross map is a sum of a ton of cross map averaged if you started from the original discrete representation. So I really wanted to emphasize that although we arrive at something discrete, it is completely different from the discretization of the continuum trajectory. Of the discrete theory that was giving the continuum theory as a limit. It's really different to, maybe one way to say it is take a random walk, scale it, you get the Brownian motion, discretize it, you get Gaussian increments. And that's not the starting point, that's a new thing. And here, we would like to describe this last thing, the equivalent of Gaussian increments. But of course, it's a bit more complicated than that, the picture.
Hi, I'm online, sorry. So just a quick question. Is it easy to see that this point that you're making about parameter estimation or max likelihood tomography is sensitive to delta T? Is it easy to actually see in the classical case as well, a priori, so that I'm motivated more carefully that this is actually a problem?
No, I don't have a very good theory argument. We just see it in our, so in this, especially for this cat qubits, we know that the coefficient that comes in front of delta T in this approximation is proportional to the number of photons or the number of photons squared. And so if we have a lot of photons in the system, we see that the term proportional to the next, so to the error, the delta T squared term is very large. And that's why this approximation is bad. But at this stage, I would just like to say it's empirically, we see that for certain type of problem in cat qubits, so qubits made from coherent states, this starts to be a problem.
Sure.
Empirical point. So let's stay at the empirical level here. And okay, so the setup I want to consider is just assume you have this continuum signal. Then I assume, which is a tiny bit of an idealization, that it is binned with very flat windows. So I average it over a certain period of size delta T with a perfectly flat window. That gives me a discrete point. I do another flat window, I get another discrete point. In practice, there are on top some exponential filters, but I'm going to assume, at least for the discussion, that they are a negligible extra and that these windows are fairly sharp. And so all we know is this signal. All we know are this discrete point. It's not allowed in my game to come back to this. It's gone, okay? We cannot know the true state. The true state is only known, I don't know, maybe to nature itself, but it's not accessible since we have less information. We have only average information. Okay, so what can we do about it? I think the most important thing in this work was just for us to understand what is the right thing to define, and it's a fairly trivial thing. So it's sort of the binned conditional state, which is the stochastic average of the true state, which is not known to us, average conditioned on what we measured. So what we measured are just these signal averages. We can condition on them, and then sort of we average over all the possible signals that would have given these specific averages. Okay, I say clearly this is the best one can hope for. I think it's easy to convince ourselves that we are really conditioning on all we have, so that's the best Bayesian object you can construct. Since the bin conditional state is a bit long, so in French we devised a name for it, so we call it robinet, which means faucet. So it's because bin ro in French you can say robinet, and so that sounds like robinet. And so now I will call this state, sometimes I will make an effort to say the bin conditional state, but sometimes just robinet. Okay? And our method is going to be called robinet. Okay, so there are 3 steps. So the bottom line is that we can find an explicit formula for this guy. Okay? And that is tractable. So to derive it, it's as usual for the stochastic master equation business. So here's my definition. The first step is to use Bayes' rule. But first, you use the Markov property. So instead of conditioning on all the signals, you condition on the last signal and the state before. You can convince yourself this is really the same expectation value. And then you use Bayes' rule. So to condition on the signal, you take the average without conditioning on the signal and take a Dirac delta for the value of your signal being equal to what you measured. So maybe some mathematicians here are starting to bleed from the nose seeing these deltas in expectation values, but you can replace that by test functions, and this can be made nicer, okay? This is the physicist version, but I think this can be put in fully rigorous grounds with only Ito calculus. Okay, so this is just Bayes' rule. The next step is that this is a Dirac delta, and Dirac delta are super inconvenient, but oh, sorry, I went too fast. We can just write the Dirac delta in Fourier space, which is going to convert this Dirac delta term into a Fourier transform of an exponential of the signal. And if you remember Pierre Guillemin's talk, we can compute expectation values of exponentials of the signal. And the tool for this is the tilted Lindbladian. So if you introduce what I call the p-tilted rho, which is rho multiplied by an exponential of the signal, and then you take the expectation value. What you can show is that using repeatedly Ito's lemma, you can show that it verifies this deterministic tilted Lindblad equation. So this object can be obtained at a cost that is similar to the cost of obtaining the average state with the Lindblad equation. It's not more expensive. And if you put these 3 steps together, what you get is the exact cross map to go from the state at k-1 to the state at k. As usual, you give first the Krauss map unnormalized, and the real state is the unnormalized divided by the trace of the unnormalized. So let me unpack this a little bit. So this is just a formal notation, time-ordered exponential, to say the solution of this tilted Lindblad equation with this as initial state. Okay? Physicists love writing time-ordered exponential like this. Mathematicians usually prefer saying it's the solution of the differential equation. If the Lindbladian was fully time independent, which is probably what I should have considered here in this presentation, you just remove the time ordering and it's a regular exponential and there is no problem. So it's just this, you have to take the solution of a differential equation and integrate it over all possible values of p over the reals. So this formula is exact. It's a completely abstract formula at this stage. And you can ask, of course, is it numerically tractable? It is not analytically solvable, okay? I cannot split a formula that whatever L and C gives me the solution. So is it numerically tractable? That's what we care at the end, okay? And like all the exactly solvable problems are either already done or uninteresting. Okay? So this is a good sign that this is not solvable. Okay, so it's an integral, so that looks like a problem. But as you know, or probably know, is that one-dimensional integrals of smooth function are always numerically exact. So in the sense that if you take 100 quadrature points, this is equal, the integral is equal to the sum with carefully chosen weights to machine precision. Okay, if you take Gaussian quadrature of a smooth function, so in our case, we will take 32 points and we are numerically exact, like adding extra points doesn't give new digits. I think it's important to have in mind that exact form for integrals are very useful in more than one dimension, but in one dimension, these numerical formulas are usually faster than the analytical forms. So well, we just do this. So in our case, this is the form we have, we include this delta TP squared here into the measure, which allows us to use a Gauss-Hermite quadrature, and this replaces this integral by a sum. I'd like to insist that it is technically an approximation in the mathematical sense, but in terms of floating point precision, this is an exact statement. Like, there is really no difference. You wouldn't know that this was approximated. And this is just a solution of a linear ordinary differential equation. So what we have is roughly, we have to solve this ordinary linear ODE, this linear ordinary differential equation for roughly 100 points. In fact, in practice, we realize that even with around 30, this is essentially exact. And this is the exact version of Robinet, so we can do a quick test. We take a qubit. So the first step is to check that the signal probability is correct. So if you take the trace of this Roca tilde, it gives the probability that you would have obtained this signal. And so we compute in red with our method the probability of this signal for a qubit where sigma minus is continuously measured, eta equal 1, and we start in the excited state. And the exact model doesn't matter so much. And we compare it with the empirical average for 10 to the 6 very fine-grained trajectories. And so the histogram is the Monte Carlo method with a very, very fine discretization that splits our time bin into many, many small time bins. Then we make the statistics at the end, and we compare with our exact result, which is in red. And so the fit is very good, and we tried various, like dozens of models like this, and you see that the fit is very good. Maybe some point about numerical performance to give Pierre has a very nice poster on this code he co-developed called Dynamics. So if you want to do the Monte Carlo version, it takes QTIP 10 minutes. With Dynamics on CPU, it takes 20 seconds. With Dynamics on GPU, it takes 0.7 seconds. So that's to get the blue histograms to compare. If you take Robinet and 32 quadrature points, it takes 0.5 milliseconds. So these plots are absolutely instantaneous. You can change all the parameters, plot them instantly. And so that's very convenient. So for example, you can change the efficiency, see how the plot changes sort of instantly. If you want to plot this for a million different efficiencies, it's possible, okay? Like everything is fast. So now we can compare something a bit better, is that we simulate a quantum trajectory with Robinet, with the Rouchon method, and with the Euler method. We take fairly coarse time bins. So we take a time bin that is too large for Rouchon and Euler, like it's unwise. And we compare the fidelity with the true state, and the true state, again, is optimized with something, obtained with something very fine-grained. And we consider a process that is known to be hard to simulate, which is the deflation of a coherent state with 2 photon loss. So the original state is like this. It's deflated, so it's losing photons pair by pair from the coherent state with alpha equals 3 down to this almost converged state. And what we see, and then we compare the fidelity of our various simulation methods to the true state. And if you take the Euler scheme, so actually it's not strictly the Euler scheme we are using, like a half-order Rouchon improvement of the Euler scheme, still it gets absolutely destroyed. So instantly the fidelity is at 0. Then you take Rouchon method, which is again a pretty good discretization method, usually also gets very bad before it reconverges. And Robinet is here. So it's the fidelity remains very good, and it remains qualitatively correct throughout. Again, there is no way to get fidelity 1. Information was lost. But what we claim is that this is the best you can get. Okay, this is a Bayesian optimal, and that there is no way to get better than this curve, and the method gives it, in fact, for fairly cheap. Okay, because what I call at 1 is really, if you like, the God-given state reconstructed with the fully continuous signal, no binning. So I know only the average of the signal over the time bin. So there is no way I can reconstruct exactly the state, but I can get closer to, if you like, having averaged is a bit equivalent to having lost a bit of efficiency. It's not exactly, okay, it's not a strict equivalence. Like fairly intuitively, this is an effect that's close to having lost a bit of signal. This is because there are stationary state effects. So it's very common for these numerical methods to get destroyed in the transient and go back better at the end. Because at the end, you are absorbed by the stationary state, and so you get less dependent on all that happened before. This is fairly common at least for this type of problems. You see that with most numerical methods. And some methods never recover. But some decent-ish methods, at least you see that they go back to the stationary state. Okay, so that's what. Okay, I think it's good also to see that qualitatively this trajectory is very reasonable. So now we do something that's a bit stupid, is that we re-average over the signal a posteriori to go back to sort of the Lindblad. Okay, so this is the true state, the Wigner function with the true Lindblad equation. And these are sort of the stochastic description that we then average. But this is to compare, to see at least do we recover Lindblad, okay? So Euler is gone, you know, in some weird space very quickly. Rouchon is first creating fringes that don't exist and then more or less reconverging. And Robinet and the true, although the fidelity is not 1, it's 90%, they look qualitatively the same. If you zoom in, you realize that the Robinet state is a bit less pure. It's a little bit more spread, which again, intuitively, we relate to the fact that we have averaged the states a little bit, averaged the signal, sorry. Okay, so this is all based on quadrature. This is exact, but it's quite useful intuitively to see how it compares to discretization schemes. And to this end, doing a perturbative calculation is useful. So we can do an expansion of the Robinet result in powers of delta t, in powers of the bin size, to see what new contributions it gives. Since I spent quite some time, I will go very quickly. So you have to be very careful how you do this perturbative expansion in delta t, because the signal itself is of order root delta t. So this is the usual business that you have to rescale everything so that everything is of order 1, and then you Taylor expand like a madman. Okay, but first you have to make this rescaling. So I assume a time-independent Lindbladian. I start from this, where I did these rescalings, and now the delta t dependence is only in the exponential. This stuff I can Taylor expand, okay? And then I can integrate over this kernel the things that I Taylor expanded. That's fairly easy. This is what I get from Taylor expanding to order 4, okay, so to order 2 in dt, order 4 in root dt. And now these integrals you can do exactly because they are Gaussian. Okay, they are Gaussian integrals. I do the Gaussian integrals, and I get the expansion of the filter to various order in delta t. This is the usual signal-dependent term in the Euler discretization of the stochastic master equation. This is the usual Lindblad term in the discretization of the stochastic master equation. To lowest orders, this guy is 0 on average, so doesn't contribute to the lowest order. That's why you get the Euler SME. And these are the next terms, and I have a harder time giving them an intuition, except that they refine the result. Okay, they make the state closer to what we need. Okay, so on the formal side, that's all we have. So we have an exact method with quadrature, and we have this perturbative expansion. So here I stopped at order 4 in root dt, but in principle there is no objection to go to very high order. And since we are expanding, we are expanding the small part of the exponential that has the lowest powers in EU. So this expansion is also convergent. It's not a 0 radius perturbative expansion. If you refine this perturbative expansion, in principle, it converges even for large delta t. But for large delta t, we recommend you use the quadrature version that is fully non-perturbative. Okay, last point maybe is that so far I considered the problem of reconstructing the trajectory given experimental results. And this is really a reconstruction problem. But you can also sample with this method. So now that with this method, you can compute the probability distribution of the signal. With the perturbative expansion, it's a polynomial of order 4 times a Gaussian. And okay, there are known techniques to efficiently sample from such probability distribution that are almost rejection-free. So it's very efficient. And so you can also use this to generate trajectories. So I'm wondering also, like a question for Howard, how does it compare, how does it fit the criteria put forward recently in this paper for what is a good discretization of the SMU? Because in fact, it gives a sort of discretization. If I have 1 minute, I give
3-4 minutes.
Okay, I give what I think is an interesting experimental thing we could do with this, is that there is a subtle point here that has been, I think, very well discussed in Benjamin's talk, which is how do we know all this business is correct at the end? Like this theory of quantum trajectory is correct. The ideal test would be you take the full signal trace, you condition on this, and you repeat many times the experiment to get exactly this signal trace. You post-select, and then you do tomography of these states. And this, if they match your quantum trajectory prescription, you know the theory is perfect. But okay, this is totally infeasible because the space of possible trajectories is exponentially large in the number of bins. And what Benjamin presented is a very powerful test, which is instead you condition on your predicted observable value, and then you projectively measure sigma z to compare, and you get these very nice fits. And it is a very powerful consistency check, and as far as I know, this is the best test currently of the whole theory. Now, of course, I'm going to nitpick a little bit, but I still think it's an excellent test. Okay? One thing that we can nitpick is that it cannot, in principle, falsify a poor use of the signal. So what I could do is I could take the signal that Benjamin got, I could mix it with noise, and then reconstruct the state with a SMA with lower efficiency. And this would still totally fit these plots. So you can show that your theory is perfectly consistent, and then you can try to maximize your efficiency, which would be pretty convincing that you are washing the signal of all its information. But okay, I could still spoof it in a way by saying, okay, at least I have a worse theory, like this is a much worse theory, that would also pass this test. I think with this bin version, we could go back to the stronger test in principle and show that there is really no Bayesian juice that you can extract from the bin signal at least. So you consider just one or a few large bins, but since it's Markovian, in principle, you could just take one bin and then condition on the bin values of the signal, you do a state tomography. Then you compute the quantum trajectory prediction Robinet. But I insist, the conditioning here is independent of your reconstruction method. That's the difference. Then you compute the corresponding state Robinet, and then you can compare these two states for various signals and initial states. And this is really a proof that we wash everything from the signal. Like any suboptimal use of the signal would give, in principle, lower fidelity. Okay, would show you that maybe you're consistent with the previous test, but you are underusing the information contained in the bin. And the crucial thing is really that we condition only on the bin, on the signal itself, and not on anything that comes from our very theory. So the way we group the rows together is theory independent. And that's why it's not just a consistency test. Okay. So this was the last point, and I leave you with this summary of what I just said. It's just a summary, nothing new.
Okay, let's thank Antoine for this wonderful talk. And we have time for a couple of questions.
Hello. Thanks for the talk. So my question is, what defines the bound of the fidelity of this Robinet state? Because we are looking at the average time bin. So if can the fidelity be improved if we increase the number of the trajectories?
Okay, so this fidelity, you mean in the, okay.
with the true state.
This I go back to. Okay, I think it's slow, so I might take forever. Okay, this, for example?
Yeah.
Yeah, this is the average fidelity of the stochastic state. So there is the true stochastic state. There is the one I reconstruct with Robinet. I look at their fidelities, and then I averaged over new possible realization of the experiment, and then I plot this average fidelity. Actually, Pierre plotted it.
But I'm asking, if we increase the number of trajectories, will the fidelity be improved?
No, this is supposed to be converged as a function of the number of trajectories.
Right.
Yeah.
Thank you so much.
If you want, this even our estimate of the fidelity has some Monte Carlo noise in it, but in principle, this is very small in this plot.
Thank you so much.
This? No, that was the fidelity. No, you're right. Here it should agree exactly. Yeah. Right. Yeah, it should agree. Yeah, it should agree exactly. Yeah, it's here. It should agree exactly. Sorry. Yeah. That was what I said was wrong. You're right. Yeah. My mind was still on this plot when I said that. Yeah.
Hi, Antoine. Sai here from IIT Bombay again. Thank you for this lovely talk. Can I just ask you, have you tried, so I have two quick questions. One is, have you actually tried parameter estimation using the Robinet method, and do you see kind of improvements? Is there a plot, or could you just comment on that? And this is number one. Number two, have you tried using qubits as opposed to kind of coherent states, essentially get out of the Gaussian kind of structure to kind of see whether this whole thing works?
Okay.
I just want, yeah, thank you.
Okay, so no, so here by qubit versus like oscillator, this is really the physical Hilbert space. So what I showed works for qubits, oscillators, a bunch of oscillators, and we have tested for both. And it's just typically the oscillator case, the nonlinear oscillator case is harder numerically. I mean, that's what we see. The discretization is tougher in time.
Yes.
So that's why we tested it mostly on this. For the parameter estimation, that's a very, very good question. We have a lot of max-like algorithms that we want to test this on. This is really our next step. Our next step is to use this for parameter estimation, but we haven't tried it yet. So we haven't yet put the pieces together. So we have worked on new estimation algorithms. We have worked on this independently, and our goal is to put everything together. So I hope it's going to be nice, but we haven't tried it yet.
Could I just ask one last question as well? This is maybe an out of scope question, so you can just tell me that, that's fine. I'm interested in trying to see these kinds of improved algorithms that can also be implemented on FPGAs, on essentially low memory devices, which are basically in closed loop control. So do you know how your algorithm performs in comparison? Like, have you given consideration to this question of essentially trying to integrate it into hardware?
That's a good point. So probably the best for this type of architecture would be to use the perturbative version, because it really looks like a standard discretization scheme. So if you can already implement the known methods like, say, Runge-Kutta or Rouchon or whatever, the perturbative version at least should be implementable. The first version, exact with quadrature, is in fact more adapted to massively parallel hardware. So that's why it's so fast, because we need to solve the differential equation for a number of quadrature points. These are completely independent, so we can do that. We can batch this on the GPU, and it's instantaneous.
Sure.
So one is better for sequential, the perturbative one, fast sequential, and the first one is better probably for parallel architecture.
Oh, thank you very much.
Okay, we have time for one last question.
Yeah, thanks. Yeah, so beautiful talk, really. So I like a lot the idea at the end that you bin on larger time bins so that you can actually test maybe more rigorously. But so we agree that if you do that, the entropy mean, the purity of the systems will also decrease, right? So if,
You're right. So if your bin is too large, you're going to lose purity. Yeah.
So there must be some trade-off in the testing that you mentioned.
Yeah. So the thing is, yeah, I don't want to take a bin that's infinitesimal because otherwise nothing happens during the bin. I want a little bit of stuff to happen, but enough that I don't demolish the purity by taking an average that doesn't see any oscillation, for example. Yeah. So I totally agree. There is a sweet spot. It's unclear. I should say, I mean, for this is to some extent work in progress. I mean, all these numerics are preliminary. We're also here if you have like good ideas about how to test this experimentally. We are very open on this right now.
Okay, congrats.
Okay, let's thank Antoine again for the talk and for answering all the questions.